Section 5.1, extreme values of functions. So what we are going to be doing today is starting to dig into the analysis that leads us to finding maximum mins for functions. And if we look at this first problem, which we're not going to solve, but we will by the end of this chapter, we've got an automobile's gas mileage as a function of many variables, including road surface, tire type, velocity, fuel octane reading, road angle, and the speed and direction of the wind. If we look only at the velocity's effect on gas mileage, the mileage of a certain car can be approximated by this function, where v is the velocity. At what speed should you drive the car to obtain the best gas mileage? Sorry, best gas mileage. So we are trying to optimize the gas mileage, or to maximize the gas mileage. Get the most miles per gallon of gas. And so we will use calculus to analyze this function to find out what velocities you should drive at to get the highest gas mileage. So we'll be looking at things called global or extreme values, local or relative extreme values, and then how to find them. And finding maxes and mins using calculus. All right, so to do that, let's just look at a simple, a simple function, and let's identify some terms that we need to know. So we have a polynomial here, which looks like it is what? Describe the polynomial. Talk about degree, talk about possible degree, even, odd, moderate. It is even. A positive coefficient out in front on an even function. Possibly what degree? Possibly fourth degree. So how do we know it is even? Tails go in the same direction. How do we know it has a positive coefficient out front? Opening up. Okay. And why do we say fourth degree? So fourth degree looks like even quite often, right? Yes, that's why. All right. So what we're going to do is use this kind of nice little easy function to identify some terms. And before we even get to the key terms, I want to talk about critical points. So if we look at this function, and we're going to start talking about maxes and mins, okay, you can see that we have how many minimums do you see? You see two minimums. And if we look at our terms, absolute and relative or local minimums, how many absolute minimums do you think we have? Okay, Spencer, Brendan, Jenica, Madison, and Brandon. Come get these. All right. So you're telling me it looks like, just from the term itself, it looks like we have one absolute maximum. Well, we do. And when you think of an absolute maximum, that is the biggest possible value out of all of the y values for the function. Right? It is the highest. So the absolute maximum is the highest of all the maximums. All right, and then an absolute minimum would be the lowest, and we're looking at y values when we talk about these absolute maxes and mins. The lowest of all, the minimum. Okay, and we want to remember we're talking, when I ask for a maximum, I'm asking for the y value. Same with minimum. All right, how about a relative or a local minimum or maximum? So if I'm talking about a relative or local maximum, and it's the highest in what I would call its neighborhood. It's the highest in the x values around it. So we would say a relative max or a local max is the highest in its neighborhood. calculus. And a relative or local minimum would be the lowest of the two. And when I say neighborhood, I mean just look immediately to the left and immediately to the right of that point. Okay? All right. So, tell me about the derivative, because now we'll dive into calculus. Tell me about the derivative at any of our maximums and minimums that we see here. The derivative is 0. So if I draw in the tangent line here, it's horizontal, tangent line here is horizontal, tangent line here, use the line. Is horizontal, and I will attach it. There we go. Okay, so then we could say at maxes and mins, the derivative should equal what? 0. Are there any other cases where we could have a max or min where the derivative would not equal 0? Can you think up?
On the right-hand system,
Nope, because there is no point that we can identify. So in this case, this function actually does not have an absolute max. Okay, but think of other shapes of graphs. So we have a maximum where the derivative would not equal 0. Gabby? There we go. So if we have a function that looks like this, we still have a maximum, correct? But the derivative does not equal 0. The derivative is what? Undefined. So we define the term critical point to be the x values where the derivative equals 0, and the most forgotten because people get caught up in the equal 0, or is undefined. We call these critical points because these are points where we could have a max or a min. Okay, so if you have a max or a min, it will happen at a critical point. All right? Are we okay with that? Charlotte, it is Friday morning. Thank you. Okay, we're good. All right. So now I want you to work on this sheet. We're going to identify a lot of different things about this kind of funky function. And we'll get practice at looking for critical points, maxes, mins, and so on. And then once we get through this sheet, we will do one example. Really, I'm not pressing a button, I swear. I wish it would stop. Just give me a second. All right. Okay. So, as I was saying, once you finish this worksheet, we will do one example, kind of an extended example about finding maxes and mins. We're going to start with absolute maxes and mins, and then we'll move eventually to finding relative maxes and mins. So, with your partner, please go through this, and we'll look at the solution to this when you are done. So we're asked to find the extreme values of this function, which is a piecewise function, and the first thing I want you to do is sketch this piecewise function. When possible, it's always nice to think visually. This one's pretty manageable, so take a minute to sketch the function. All right, do you agree with us with the sketch? Not quite done yet? Hold on. Move forward. I have my steps, so we agree with the sketch. Hang with me through. But, Boris, get that head up. Almost. There we go. All right. So, when we sketch this, and with a piecewise function, it's always good to think, do I know if this function is continuous or differentiable? Well, we just graphed it, and we see that indeed it is continuous, correct? But I want to go through the little analysis anyway, because on your test, there was one part quite often left off when you had to show me something was continuous. So, the left limit equals the right limit, yes, but also show that equals the function value. Then it is continuous. So we need the 3 lines here. There's only half. Okay, so this function is continuous because the limit from the left is 3, the limit from the right is 3, and the function value is 3. Okay? Differentiable, that means the derivative from the left has to equal the derivative from the right. So the derivative from the left is negative 4x, the derivative from the right is 1, and at x equals 1, are they equal? No. So, can you tell me where my critical points are? At x equals 0. Why? We see a maximum, but the derivative f prime of x would equal what there? Equals 0. And where else? At 1. Why? At x equals 1, because f prime of x is undefined. Okay? Or does not exist. All right, so now we have to do a little analysis. So we do a slightly different analysis for absolute extrema versus relative. So to find relative maxes and mins, the first method you're going to learn is basically called the first derivative test. And essentially you find your critical points, and you look to the left and right of them to see if the function is increasing, and then increasing, then decreasing, to show we have a maximum, decreasing, then increasing, to show we have a minimum. Okay? So, for the first derivative test, we will find critical points. You'll then set up intervals around those critical points. And you will look at the derivative to see if it is positive or negative. So if my critical points are x equals 0 and x equals 1, I want to set up intervals around them based on the problem that we're dealing with. We were given no endpoints to our interval, correct? This is an open interval. So our intervals will go from negative infinity to the first critical point, going from left to right, and then from 0 to 1, between the critical points, and then from 1 to infinity. All right, so we're determining what's happening to the left and right on these critical points. The next thing you'll see when I do this is I pick a test value that's in that interval. Pick a nice value that's easy to work with. So, what's a nice value in here? Nope, can't include 0. Negative 1 is a good one. How about here? 0.5 or 1/2 is good, and then 2. Nice, easy numbers. And you need to plug them into the first derivative to see if the original function is increasing or decreasing, because that's what the first derivative will tell us. So, our first derivative, if I am at -1, which branch do I use? The top or the bottom? We use the top. And we are looking at the derivative. So it'll be -4 times -1. Do I get a positive or a negative? I get a positive. -4 times -1. Now, on these, I only care about the sign. I don't even care about the number. That is a positive. If I plug 1/2 in, am I still in the top branch? Is 1/2 less than 1? Indeed. And do I get a positive or a negative? I get a positive. And then from 1 to infinity, what do I get? I get a positive there. Because we are plugging into that one. So on our 1/2, 1/2 squared is what? 1/4, and 2 times that, we still end up getting that. Where are we going wrong? We should be decreasing our interval negative infinity to 0, 0 to 1. Oh, thank you. We plugged into the original. Thank you. We need to plug into the derivative on this one, like we did the other. And the derivative is negative 4 times 1/2. Thank you. And we get a, thank goodness. All right. So that means the original function was increasing, then decreasing. So what do I have right here? A maximum. And then over here it is decreasing, then increasing, so I have a minimum. Now, this is the analytical process. Yes, we have a graph where we can see the maximum in, but sometimes you won't have that, and you need to find it. Okay? So we have our first derivative test where you find your critical points, set up intervals, pick a test value, and the key mistake made is people, like I did, plug into the wrong functions. You want to make sure you're plugging into the derivative. Okay? So we find that we have a max or min. This is to find relative max or min. Okay? Now, absolute max or min. Looking at our analysis here, to the left of 0, it's going down forever, and to the right of 1, it's going up forever. Do we have any absolute extremes? We do not in this case. So no absolute maxes or mins in this one. Because we, as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to infinity. Okay? If you are asked to find an absolute max or min on a closed interval, the process is just slightly different. And these should go into your notes. These are important. You'll be using them all chapter. Absolute max or min on a closed interval. So if we look at a function like this, there, and have an endpoint there, where are the places where we could have the highest of all the highs and the lowest of all the lows? So it could happen when the derivative equals 0 or is undefined, or it could happen where else? At these endpoints. So when I said you'll not be asked about relative extrema at endpoints, you won't, but you will be asked about absolute extrema at endpoints. So, to find absolute maxes or mins, you still find your critical point. And then essentially all we need to do is look at the y values at each of these critical points and endpoints to find the highest of all of them and the lowest of all of them. So we're going to look at the y values at critical points and endpoints. There's the most forgotten part, is on a closed interval everyone forgets to check the endpoint. So underline it, star it, do what you have to do to remind yourself that an absolute max or min can happen at critical points, and it can also happen at the endpoint. So simply find the critical point, and then plug those x values into the function to see which one is the biggest and which one is the smallest. Okay? All right. I think that's all I have. All right. So, homework for tonight. Roll it up.